intro to what WebAssembly is for those of you who don't know. I'm going to give you an intro to the project we've been working on, Wasmjit-omr, we call it. I'm going to go into a couple of implementation details, how we went about testing it, and then a bit of future work that we plan to do. So what is actually WebAssembly? Well, it's designed as a language for a platform-independent compiler target being run inside of a sandbox. It's designed to be quick to parse and compile into machine code for modern architectures, and it's typically used, at least right now, to run performance-sensitive code inside the context of a web browser. The story of how WebAssembly came to be is interesting. I'm going to gloss over some details, but it started off with just everyone had static HTML pages. If you were fancy, you had some server-side stuff, but eventually people wanted client-side interactivity, so through a long process of things, we ended up with JavaScript everywhere. And this was fine for a time, but early JavaScript was slow, so what do? We throw JIT compilers at the problem. And, you know, that solves the problem and everything is hunky-dory, except it's not. Developers started doing more and more with JavaScript as they discovered that the performance was better. And even with a JIT compiler running, JavaScript was still too slow in some applications on web. For one thing, every time you receive a JavaScript file, you have to parse it. And that takes a not insignificant amount of time. And its performance is also hampered by some dynamic typing problems. There are ways to get around this, but not everybody conforms to them, and it can cause performance problems if you don't. And another thing that ended up happening was that we discovered that not everybody likes dealing with browsers' JavaScript implementations. They're not all that consistent. So people would take other languages and transpile them to platform-independent JavaScript. And then people started taking JavaScript and transpiling it into JavaScript. But the problem that people ended up running into was just JavaScript didn't make a very good compiler target for a lot of languages. It was just too high level. It was too opinionated on how certain things were supposed to work. There were two solutions that people came up with in the early days for this. Asm.js, a super basic subset of JavaScript designed for high performance done by Mozilla, and Portable Native Client, or Pinnacle, by Google. So in Google Chrome, it would just run an LLVM-style bytecode. But neither of these was great. Asm.js still had to be parsed as JavaScript, and Pinnacle was always restricted to Google Chrome. So that's where WebAssembly came in. So WebAssembly is standardized across browsers by the W3C to avoid any vendor lock-in problems. It's designed for quick parsing and compilation, as quick as possible, using statically typed opcodes to perform computations with a value stack for storing intermediate values. It supports only 4 really basic primitive types, 32 and 64-bit integers and 32 and 64-bit IEEE floating point, nothing fancy there. Strangely enough, it uses structured control flow, so you'll see if-else in there. This actually makes validation a little bit easier on the compiler. And it also allows arbitrary loads and stores from a linear memory, so it's able to deal with languages like C and C++ that expose a lot of pointers. WebAssembly code you'll see will typically look something like this. So in this case, this is a function that just takes its argument. If it's the highest possible 32-bit unsigned integer, it'll just return it. Otherwise, it'll increment it by 1. But you'll see there that there's that if-else statement I was talking about, where instead of seeing branch opcodes, you'll see this. You can also write it like this. It's a little bit nicer to look at as a human. It actually compiles down to nearly the same thing, but a lot nicer to work with. But our project starts from here, and we started with the simple question of, what if we could run fast WebAssembly outside the context of a browser? And why might you want to do this? Well, you could use it to distribute platform-independent executables, even for C and C++ applications, which have tended to be very platform-specific. You can use it to test web application code outside of a browser if you design your WebAssembly code right. You could actually embed WebAssembly as a scripting language into a larger application, or if you're crazy, you could run untrusted code on the server side inside of a sandboxed, safer environment. So we actually chose to build our JIT compiler on top of an existing interpreter that was in a project called Wabbit. And we used Eclipse OMR JitBuilder to build our JIT compiler. It was worked on by myself and 3 other contributors at the time, and it is entirely open source. You can go and play around with it if you want. It's there for the world to see. You might wonder, what is that Wabbit I mentioned? It's the WebAssembly binary toolkit. It builds itself as a suite of tools for WebAssembly. Basically, it just has a ton of utilities for converting between, say, textual and binary representations. But for our purposes, the most important part is that it contains an interpreter. And it can also be used as a library, so you can embed it into any C++ application to just kind of throw a WebAssembly interpreter in there. So why did we choose this? It's relatively stable and mature in comparison to certain other WebAssembly interpreters. It's standards compliant at this point, as far as we know. It doesn't actually rely on having any JavaScript, so we don't have to deal with any of the weirdness that comes with that. It's completely divorced from that at this time. It's also written in C++, which is the language that JitBuilder currently uses. That makes it really easy for us to interface with both Wabbit and JitBuilder. And I'm going to have to go through a little bit of how the Wabbit interpreter starts, just to give everyone an idea of what's happening internally. You start off by creating an object of this type environment, which represents a WebAssembly sandbox. So that contains global state, like the memory, global variables. You register these things called host modules on it, which is basically just a really fancy term for C functions that WebAssembly code can call. You call this function called read binary interp, reads a WebAssembly binary file from disk, loads it into memory. You create this object called an executor, which represents a thread in WebAssembly. And then you call this aptly named run start function, which just starts running WebAssembly code. Just go off and do it. There's quite a bit going on under the hood here. That read binary interp function is actually doing a lot more than you might think. It has to validate the type correctness of WebAssembly code. And it also does a little bit of lowering, so it makes things a little bit easier on the interpreter when it gets to the code. So things like that structured control flow is all just turned into straight up branches. Some internal opcodes end up getting added to manage stack allocated locals, really simple things like that. Those executor objects also wrap thread objects. And there's this function called thread run that actually contains all of the code for the interpreter. And you have to set the program counter of the interpreter before you call this thing, and then you call it, it runs some number of opcodes, and then it will return control to you. And you can resume it by just calling this function as many times as you want. There is a physical value stack that is storing all of these temporary variables, and a call stack which stores the return addresses, pretty standard. There are a lot of interpreter-related functions that return this thing called a result. Basically just a fancy word for error code. If it's result okay, it was successful. Otherwise, it's some error code. Except thread run, which has this other weird code, which is result returned, which just means it finished running. For some reason, they decided result okay was for when you are suspending. Don't know why they did this, but returning anything, any result except result okay or result returned, I'm also going to call trapping just for brevity's sake. And there's this weird macro you'll see all over the place in the interpreter. It's called trap check. Basically just if the result was an error, return it. So we need to find a place to do our initialization of the JIT. So we need to set up a bunch of JIT-related data structures. And it's not entirely clear where you might want to do this. We could require that whatever program was embedding the WebAssembly interpreter manually call our functions to handle this, but this requires changes to every program that uses WebAssembly if they also want to use our JIT, which is not ideal. We could hook one of those executor functions. We could say every time you call run start function, we just initialize the JIT. Turns out people can bypass that. You can just call thread run directly. There's nothing stopping you. So if they did that, we would crash, and that's not good. We could hook thread run as well, but that's called many, many times, even within JITted code if we call an interpreted method. So adding checks there is not ideal. We could also hook creation of those environments. So every time a sandbox is created, we initialize the JIT. But we can actually have multiple of these things going at once, which can mess with the JIT because it relies on a lot of global state. We did decide on that last option, hooking environment creation. It seemed like the most logical step. But we do have to keep an internal count of how many of these environment objects are live, so that we initialize only when we're creating the first one, and we can shut down when we destroy the last one. So we just end up throwing in an extra class here that just takes care of that in an RAII style, really basic C++. You construct these JIT environment things, and as long as one exists, the JIT is initialized. And you need one of these environments to execute WebAssembly code, so you can't call any WebAssembly code without this. So we know the JIT is always initialized when we call. Another interesting problem we ran into was actually transitioning from running interpreted code to running JITted code. We did a very standard thing of just when the interpreter executes a call or a call indirect, we can effectively run that method in a JITted body instead. We decided on very simple counted compilation. So after a function is called n number of times, say 5 or something, we'll JIT compile it. And if it was successfully compiled, we don't have to interpret it anymore. We can just call the compiled code. There are interesting hacks going on here. I am going to completely gloss over them. They're not even going to be in the code because they complicate things a lot. And we're also ignoring that idea of suspending threads. It's really hard to deal with for us, and it's just out of scope of this prototype. It's not even used all that much. So we just decided for now we're going to ignore it. So originally, the interpreter code for handling call opcodes looks like this. It's just really basic. We just push something onto that call stack, and we redirect the interpreter to start executing those opcodes instead. Super simple. So all we have to do is add in a little bit of extra code that calls this try-JIT function that we have that deals with a bunch of stuff internally, and if we successfully compile, we just have to call the JIT function instead of redirecting the interpreter. One additional thing we do have to do there is we have to pop the return address manually. Usually the interpreter would do that when it encounters a return opcode. In this case, we don't have that luxury. There's all this stuff going on in try-JIT that I'm not going to go through, but it's there if you want to see it. Another interesting problem is that it's actually possible for JIT compiled code to call an interpreted function. And because of this, the interpreter needs to know when to stop. Essentially, when it normally encounters a return opcode, it'll pop the return address and keep going, which is not what we want. We want it to return to the JIT compiled code. So we have to keep this little thing around called last JIT frame, which is essentially just a value for telling the interpreter when it should return. And if the interpreter returns from that frame, it just returns to the interpreter. It returns to the JIT compiled code instead of just continuing to interpret opcodes. Another thing we have to do is we need to make sure that from the JIT code, when we set this thing, we have to store the previous value and restore it. Otherwise, JIT compiled code calling the interpreter, calling JIT compiled code calling the interpreter would break. Not something you want to debug at 3 in the morning. The original code for dealing with returns is super simple. It only returns from the interpreter if we're returning from the very last function. So we just have to add a little extra check there. Super basic. So we had two different kinds of testing going on. We had some functional testing where we wanted to test the functionality. And thankfully, we were actually able to use Wabbit's existing test infrastructure, and we were able to clone their CI setup. And from that, we could just write some new test cases that exercised the JIT. Super simple. We ended up with a lot of test cases. Unfortunately, our output didn't end up being 100% consistent with the interpreter because the interpreter was doing some weird things. Specifically with regards to the sign of not a number, spec says not important. So even though it's different, doesn't matter for our purposes at least. We also had a number of micro benchmarks that we used to measure fine-grained performance of really small sets of opcodes, and a macro benchmark that we used to exercise as many parts of the JIT as we could. Our micro benchmarks were mostly manually written WebAssembly. There was a little bit of bare metal C there that was compiled using a special version of Clang. We had iterative factorial, Mandelbrot, and bubble sort, pretty basic stuff. And we ended up with these results. So as you can see, for instance, for Mandelbrot, which is the blue line there with a variable number of iterations, we're basically always beating the interpreter. But for certain other things like bubble sort with a variable number of elements, sometimes it's not actually worth it to do the JIT compilation because it does take time, and the benefits we gain from it just aren't enough. But over time, we do always beat the interpreter. For our macro benchmark, we decided it should include a mix of floating point and integer arithmetic. It should include lots of memory access, exercise as many opcodes as we reasonably could, include lots of different functions. That way, the JIT compilation time of these functions actually plays into it a little bit. And we eventually decided on using something called a witted ray tracer that was written in C++ and again compiled to WebAssembly using Clang. For those of you who don't know what a witted ray tracer is, really, really fast introduction. We have a 3D scene. We want to make a 2D image out of it. So we start from the camera and we just shoot out a bunch of rays into the scene, find the first object they intersect. We can do other fancy things like reflective surfaces and shadows. What the specifics aren't important for this. What is important is that this is computationally really expensive to do. So it works well for our purposes. And in the end, our macro benchmark ends up with an image that looks slightly like this. So we start, the ray tracer starts by loading the scene from the disk. It has to prepare some data structures that it uses during rendering. And then it will actually render a low resolution preview, which you will see, and print it to the console. This actually demonstrates the compile time of the JIT really well. But we also render a higher resolution image of the scene, which we then save to disk. And during that process, there will be a progress indicator that will tell you how far it is along, which you'll see later. We did have some trouble getting this to work because it did use C++ libraries. It was actually not written with this use in mind. So we had to cross-compile things like compiler-RT, which provides runtime functions for any Clang-compiled code. We used Muscle for a really, really lightweight libc. And we also had to cross-compile things like libc++, libc++ ABI, and a couple of boost libraries that were actually being used by the ray tracer in that case. And on top of that, we had to implement a special version of the interpreter that handled a couple of Linux system calls. So it would emulate memory management, reading and writing to and from files, things like that. So I'm going to give a really quick demo of what that looks like. On the top, you'll see the version running in the interpreter, and in the bottom, you'll see the version running with the JIT. So you'll see the interpreter actually starts going right away. The JIT is still there sitting around compiling things, whereas the interpreter has actually already completed the preview image and has started on the full resolution render. JIT is still waiting, which is unfortunate. But you'll see that it will pick up. And once it has started going, once it's done that compilation, it actually goes much faster than the interpreter. So you'll see that progress there has already passed the interpreter after a very short amount of time. So the interpreter, if we let this run the whole way, ends up taking just under a half hour to render this scene, whereas the JIT takes between 8 and 9 minutes, which is much, much better. There is, of course, still quite a bit of future work we need to put into this before it could be used in a realistic context. For one thing, while we were in the middle of making this, Wabbit introduced some changes to how the interpreter worked, and we haven't brought ourselves up to date with that yet. Another thing is that when we have those opcodes which push and pop from the stack, we're actually reading and writing to memory, which is obviously not good in practice, but it was good enough to beat the interpreter. So what we want to do instead is to emulate that and effectively stop doing that where it's not necessary. There's also quite a few exotic and experimental opcodes that we're missing implementation for. So if any function uses these, we can't compile it. It has to run in the interpreter. Right now, we only support x86, even though in theory we could support things like Power and Z. This is due to JitBuilder limitations right now that need to be resolved. We also don't actually know whether we support Windows or not. We haven't tried it. We expect it should work in theory, but we have no idea. And we're also missing a couple of those functional tests. Some opcodes just don't have test cases right now, which is a little bit unfortunate, and we'd like to add those where possible. So that's my talk. Any questions? Yeah.
Are you supporting different levels?
Right now, no. JitBuilder right now only supports warm compilations. Yeah.
What are you using for a method count? Have you experimented with things, or given the option to have different counts?
So the count is user configurable. We have experimented with that. We've done things like trying with 0, which is really good for certain things, but because of certain weirdnesses going on in libc++, it can actually take a long time to compile certain functions, and those functions are often only called once or twice. We have played around with it a little bit, but we're planning to try out a couple of other things that would make it a little bit more robust.
Follow-up question. Is the entire interpreter running single-threaded with JIT? Like you don't have compilation threads?
So right now, WebAssembly actually doesn't support multi-threaded. There's a proposal for adding that right now, but it's not actually part of the WebAssembly spec yet. So all of this, yes, is running single-threaded.
More questions?
Well,
Yep.
one tiny little bit off topic. Is it the same ray tracing that they are talking about in NVIDIA new ray tracing card?
No. This is a slightly different thing.
No, I mean the algorithm.
The algorithm at its core, yes, it's the same, but it's doing very different things. Yeah.
Cool. All right, thanks, Ben.